Hey everyone, and welcome to this explainer. Today, we're zeroing in on a super specific but absolutely crucial topic, NCP-MCI 7.5, 7.6, Managing Cluster Fault Tolerance. And we're going to be looking at this strictly from the container angle. We're going to dive deep into the interplay between cluster, fault tolerance, and container replication factor. This is a must-know for your Nutanix certification, covering the baseline AOS 7.5. So why are we focusing so heavily on this? Well, the test writers know that out in the wild, admins constantly confuse cluster-level resilience with data-level resilience. Missing this distinction is a ridiculously easy way to drop points on the exam, and honestly, it can cause a total nightmare in a production environment. So we're going to make absolutely sure you've got this locked down. Okay, here's our game plan for today. First, we'll look at why container resiliency matters. Second, combining FT and RF. Third, erase your coding strip resizing. Fourth, some common exam traps. And finally, the key facts you need to memorize. Let's get right into it. Part 1, why container resiliency matters, and understanding that baseline. Right off the bat, to crush this section of the exam, you've got to internalize one foundational rule. Cluster-level settings alone do not magically guarantee container-level resiliency. It takes two to tango here. Let's get our acronyms straight first. FT is fault tolerance. That's your cluster-wide setting, defined the moment you build the cluster, and it dictates how many node or disk failures the whole system can take. RF, on the other hand, is replication factor. This applies directly to the storage container itself and sets the exact number of data copies the system will actually maintain. You know, it's so easy for an admin to build this incredibly robust cluster, click Next through the container setup, and just assume the data inherits that top-tier FT level automatically. But that assumption, that's exactly where the exam will try to trip you up. It's really a matter of potential versus reality. Think of your cluster FT as the architectural ceiling. It tells you the absolute maximum resiliency your hardware and metadata can handle. But your container RF, that's your boots-on-the-ground reality. Imagine you've built this massive, heavily armored castle that can fend off multiple attacks. That's your cluster. But if your container RF is too low, it's literally like taking your most prized treasure, your application data, and leaving it in a flimsy cardboard box right in the middle of the courtyard. The castle walls might hold up fine during a siege, but your treasure, yeah, it's still getting destroyed. Moving on to Part 2, combining FT and RF, looking at some concrete examples. Let's see how this actually plays out in the real world. Say you've meticulously designed a highly resilient setup with 2N/2D fault tolerance on your cluster. You're expecting to withstand 2 simultaneous node or disk failures. You're probably sleeping pretty well at night, right? But wait, what if you left the storage container replication factor sitting at 2? What happens when those 2 disks drop? Well, because the container only ever had 2 copies of that data block, if the 2 disks holding those exact copies fail at the exact same time, boom, you lose both copies. So even with that beast of a cluster, your data only survives a single failure. You've artificially bottlenecked your own fault tolerance. Nutanix documentation literally spells this out, so you know it's a prime target for the test. If you see a 2N/2D cluster mentioned in an exam question, alarm bells should go off in your head, and you immediately need to look for replication factor 3. Nutanix strongly recommends RF3 for containers on 2N/2D clusters, because if you don't bump up that container's RF to 3, you just aren't getting that dual failure protection for the data itself. The cluster's metadata survives, sure, but your actual data simply doesn't. All right, Part 3, erasure coding strip resizing and its configuration impact. Let's switch gears a bit and talk about erasure coding, or EC, and specifically what happens when you mess with your cluster fault domains on a live running system. So EC is a total game changer for saving space. Instead of taking a full 100% copy of a data block like standard RF does, EC uses parity WAF to rebuild data if a disk fails. This stacks on top of dedupe and compression, and honestly, admins love it because it saves a ton of money. But here's the catch, and it's a big one. Erasure coding efficiency relies heavily on exactly how your cluster's fault domains are laid out. Put your exam hat on for a second and think about this scenario. You've got a cluster, EC is running beautifully, saving you loads of space. Then you decide you want more fault tolerance, so you enable rack awareness. What actually happens to your usable capacity in that exact moment? Take a second and really think about it. Well, here's what goes down under the hood. Enabling rack awareness forces the Acropolis operating system, AOS, to immediately rethink where all your data lives. It literally has to unpack your existing EC strips so they comply with the new physical rack boundaries. And because it has to unpack them back into standard, full data blocks during this process, your cluster is going to experience a sudden, massive storage usage. Essentially, your storage temporarily bloats. If you aren't expecting it, this is the exact moment you get a minor heart attack as your capacity alerts start turning red. Once everything is unpacked, the system recalculates and repacks those strips to fit the new layout safely. Let's throw some actual math at this for the exam. Say you've got a 12-node cluster running EC without rack awareness. It's likely using a super efficient 4/2 strip size, 4 data blocks, 2 parity blocks. But then you enable rack awareness across, say, 6 racks with 2 nodes each. AOS is forced to shrink that strip. It dynamically drops to a smaller 2/2 strip size, just 2 data and 2 parity. EC is still on, sure, but because that strip is smaller, your permanent space savings won't be nearly as good as before. You are making a conscious trade-off here, sacrificing capacity efficiency for better physical fault domain resiliency. Section 4. Common exam traps, and those tricky edge cases you need to watch for. Test writers absolutely love edge cases, so let's call these out before you take the exam. First trap, the 1N and 1D setup. This one's weird. When you create a cluster with 1N and 1D FT, it actually defaults the storage container to RF3 automatically. But here is the kicker. Erasure coding is explicitly not supported under a 1N and 1D cluster. It will just flat out reject it. Second trap, the upgrade illusion. Imagine upgrading a 1N/1D cluster to 2N/2D. You might think, awesome, all my data is triple replicated now. Absolutely not. Raising the cluster FT upgrades the architecture, sure, but AOS doesn't just invent a third copy of your data out of thin air. You won't get that third copy until you log in and manually hike up the RF for that specific container. Finally, Part 5. Key facts to memorize for a high-retention summary. As we wrap this up, there are a few hard numbers you just have to know cold for exam day. First, you need a bare minimum of 4 nodes just to enable erasure coding on an RF2 container. Want EC on an RF3 container? You need at least 6 nodes. What about fault tolerance? To configure 2N/2D FT on the cluster, you must have a minimum of 5 nodes. Why? Because you need those 5 nodes to maintain a strict quorum for your metadata. Underneath the hood, Cassandra and Paxos need a majority quorum to survive a double failure without causing a nasty split-brain scenario. And lastly, remember that AOS dynamically calculates those EC strip sizes based on your hardware. Don't try to manually force a larger strip size. If you do, you're going to massively increase the computational overhead and drastically slow down your rebuild times. So it all boils down to this. A highly resilient cluster means absolutely nothing if your storage container isn't configured to match. The cluster might be your heavy foundation, but the container is what's actually holding the treasure. If you keep the container angle in mind for everything you do, you are going to absolutely crush this section of the NCC-MCI 7.5 exam. So taking everything we just talked about into account, how are you going to design your next fault domain? Keep studying, keep labbing it up, and I will see you in the next explainer.